Welcome to the Explainer. Okay, let's dive right in and uncover the fascinating, high-stakes story of a biological infiltrator that is literally wreaking havoc on global agriculture and totally rewriting the rules of veterinary medicine. I want to start with a question that really highlights the sheer scale of the problem we're looking at today. What invisible enemy could possibly cost global agriculture over $780 million every single year? Well, the answer forces us to look really closely at two specific pathogens, Mycoplasma gallisepticum and Mycoplasma synoviae. $780 million. I mean, that is a staggering number, right? And that annual global economic burden is attributed to just one of these pathogens. But where does this massive financial hit actually come from? Well, it's driven by precipitous drops in egg production, impaired feed conversion, elevated flock mortality when it mixes with other infections, and just massive carcass condemnations right there at the slaughterhouse. Now, this wasn't always a global crisis. It's fascinating to see how this builds from a localized turkey illness back in 1905, when Dodd first described a strange episodic pneumoenteritis causing severe head swelling in English turkeys, to what it is today. By 1943, Delaplane and Stewart had formally identified the causative agent of chronic respiratory disease in chickens. Fast forward to today, and these pathogens are explicitly listed by the World Organization for Animal Health as notifiable, economically critical diseases worldwide. Here's our roadmap for today's Explainer. We're going to cover the billion-dollar bird threat, the anatomy of a stealth pathogen, how the infection spreads, devastation in the flock, diagnosing the invisible enemy, and finally, the fight for control. So part 1, the billion-dollar bird threat. Moving on to part 2, anatomy of a stealth pathogen. Now, what's really interesting about this next part is how these bacteria operate like highly trained infiltrators. The crucial point here is that these mycoplasmas belong to a class called molicutes. Their defining feature, an absolute complete absence of a peptidoglycan cell wall. Instead, they rely on a cholesterol-rich, triple-layered plasma membrane. So by discarding that heavy outer armor, the cell wall, they become highly pleomorphic. That just means they can shapeshift, morphing from round to flask-shaped structures. They're actually the smallest known self-replicating prokaryotes on Earth, which is kind of wild. And this brilliantly illustrates why throwing standard antibiotics, things like penicillin or cephalosporins, at this enemy is completely useless. Those drugs are specifically designed to target cell wall synthesis. So without a cell wall to target, the mycoplasma basically just ignores the medication entirely. But their stealth goes way, way beyond just missing a cell wall. Once they use specialized structures to attach to a bird's respiratory tract, they constantly change their antigenic disguise. They use a family of surface lipoproteins, specifically the VLHA family, to rapidly alter their profile, which lets them easily evade host antibodies. And if that wasn't enough, they can actually hide directly inside the host's own non-phagocytic epithelial cells. That lets them establish lifelong infections, totally shielded from both the immune system and most antibiotics. Plus, they form these highly resistant biofilms. Okay, part 3, how the infection spreads. Once we understand their biology, we really have to look at how they breach farm perimeters. Now, you might think a bacteria without a cell wall would be super fragile outside a host. And generally, yeah, they are. But surprisingly, this pathogen can survive 3 times longer on synthetic hair, up to 9 days, than on natural human hair. They can also hang around for days on avian feathers, wood, and rubber, which means everyday farm personnel, their clothing, and their equipment are easily turned into unwitting biological vectors. But their most devastating transmission route isn't horizontal, it's vertical. It's a tragic cycle, really. First, an infected hen's reproductive tract becomes colonized. Then, the pathogen is actually shed directly into the forming hatching egg. That infected embryo incubates, and when it hatches, the new chick immediately spreads infectious respiratory aerosols to its immunologically naive flockmates. This trans-ovarian transmission allows the bacteria to completely bypass physical farm biosecurity by basically hitchhiking inside the next generation of chicks. That brings us to part 4, devastation in the flock. Let's look at the clinical side and examine the actual carnage this pathogen leaves behind once an infection takes hold. For egg producers, Mycoplasma synoviae causes a specific, nasty pathology called eggshell apex abnormalities, or EAA. Advanced imaging shows a catastrophic 64% reduction in the mammillary knob layer of the eggshell, strictly confined to the top cone of the egg. This structural reduction causes devastating fragility. extreme shell thinning, and increased translucency. The result is a massive spike in breakages during gathering and transport, which obviously leads to immense financial losses on the packing floor. And for the birds themselves, the respiratory impact is incredibly severe, quickly building into chronic respiratory disease. Normal, healthy tracheal mucosa measures about 49 micrometers, but following infection, it undergoes massive thickening, expanding to over 546 micrometers. By contrasting the healthy microscopic structures against this catastrophic tenfold tissue expansion, which is driven by intense lymphocytic infiltration, we can truly visualize the severe immune dysregulation these tiny pathogens trigger.
Part 5. Diagnosing the invisible enemy.
With an enemy this elusive, how do veterinary diagnosticians actually spot the infiltrator? Because the birds become lifelong carriers, diagnosis is tricky and requires a multi-tiered approach. Diagnosticians use the rapid serum plate agglutination or SPA test for quick flock screening, but it's notorious for false positives. The traditional gold standard is cultivation in specialized phrase media, but since mycoplasmas grow so slowly, that can take weeks. That's exactly why the modern industry relies heavily on rapid PCR assays and advanced DIVA systems, which stands for differentiating infected from vaccinated animals. This lets them instantly separate harmless vaccine strains from aggressive wild-type field strains, helping them outpace the spread. And finally, Part 6, the fight for control. Okay, let's dive into the strategic, multi-pronged counteroffensive. When strict biosecurity just isn't enough, we turn to vaccines, and farmers have to carefully weigh their options here. On one hand, live attenuated vaccines, like the F strain, stimulate strong local immunity in the respiratory tract and physically crowd out wild strains. But they carry risks, including horizontal spread to neighboring farms. On the other hand, inactivated vaccines offer incredible safety and zero lateral spread, but they are highly expensive and labor-intensive because they require individual injection for every single bird. Now, when an outbreak does happen, we have to use targeted antimicrobials. Since we already know cell wall drugs fail completely, the veterinary counterattack requires really precise pharmacokinetics, targeting protein or DNA synthesis instead. For instance, macrolides like tylosin are favored because they rapidly reach the respiratory tract and offer a zero-day withdrawal time for eggs, so farmers don't have to throw away their product. Alternatively, pleuromutilins like tiamulin are uniquely capable of concentrating deep inside the forming eggs to literally chase the bacteria and sterilize the yolk, aggressively halting that vertical transmission we talked about earlier. But this brings us to a terrifying reality check regarding our chemical arsenal. To quote directly from the research, the global, often indiscriminate use of antimicrobials in the poultry industry has triggered a sharp, alarming escalation in antimicrobial resistance among field isolates. Mycoplasmas mutate much, much faster than conventional bacteria. The pathogen's rapid shape-shifting isn't just tricking the bird's immune system, it's rapidly mutating to survive our most potent medications. These high mutation rates have pushed the required concentration of drugs, the MIC90 values, to exceed 64 micrograms per milliliter for once reliable medications. This is forcing a desperate shift toward antibiotic-sparing therapies, like plant-derived essential oils, to disrupt the bacterial biofilms without triggering even more resistance. I'll leave you with this final thought. As these stealth pathogens mutate faster than our chemical weapons can adapt, how will we defend the delicate balance of our global food supply? The battle against avian mycoplasmosis isn't just some niche veterinary puzzle. It is a high-stakes race for the future of global agriculture, requiring constant innovation and unwavering biosecurity. Thanks for joining me for this explainer, and keep questioning the microscopic world around you.